In this unit, I'm going to build some theory from MapReduce algorithms. This theory will eventually lead us to some lower bounds, and that in turn lets us assert that particular algorithms are as efficient as a MapReduce algorithm for a problem can be. There are several ingredients to the theory. First, we need the notion of reducer size, the maximum amount of data that a reducer can have as input. We also need the notion of replication rate, the average number of key-value pairs generated by a mapper on one input. One goal is to prove lower bounds on the replication rate as a function of reducer size. That is, the smaller the reducer size, the bigger the replication rate. Another essential ingredient to the theory is the mapping schema, a description of how outputs for a problem relate to inputs. We characterize a problem by its mapping schema, and we use the properties of that schema to put an upper bound on how many outputs can be covered by one reducer with a given reducer size. That, in turn, lets us get lower bounds on replication rate as a function of reducer size. We're now going to introduce a model that lets us discuss the best way to trade off communication for the number of reducers used. The elements of the model are simple, but the conclusions are interesting. There is a set of inputs. In the drug interaction example we just talked about, each drug and its megabyte-long record is an input. And there is a set of outputs. The output for a pair of drugs is the conclusion whether there is a statistically significant interaction between those two drugs. And there is a many-to-many relationship between inputs and outputs. Each output requires certain inputs to compute its value. In the drug interaction example, each output pair, say ij, is related to two inputs, I and j. It is common for outputs to depend on two inputs, but there are important examples where outputs depend on many more than two inputs. Often the inputs are sent as values in key-value pairs to the reducer where the outputs that need them are computed. However, in other cases, the key-value pairs could be computed in some complex way from the inputs. We don't need to distinguish these cases. We connect an input to those outputs such that the mapper for that input creates some key-value pair necessary to compute that output. Here's what the many-to-many mapping looks like between inputs and outputs for the drug interaction problem with 4 inputs. In this case, there are 6 outputs, each corresponding to one of the 6 pairs of drugs. Here's an example where outputs depend on very many inputs. We want to multiply n by n matrices. There are thus 2n squared inputs, one for each of the elements of the 2 input matrices, and n squared outputs, one for each element of the result matrix. Okay, look at a single output, say in row I and column j. If you remember your matrix multiplication, you know that this one output is computed by taking the dot product of the ith row and the jth column. Thus, each output is related to 2n inputs. There's a subtlety in our model that is not apparent from the examples of drug interactions and matrix multiplication. In these cases, the input set is fixed, and the output values depend on the inputs, but which outputs are made is also fixed. But in some important examples, what we call the inputs and outputs are really an envelope encompassing all those hypothetical inputs that might occur in some run of the algorithm, and all the outputs that might be made depending upon what combinations of inputs are present. In an execution of the algorithm, the actual inputs are a subset of the hypothetical inputs. A hypothetical output is made if and only if it can be made from whatever inputs are available. In some applications, we can only make an output if all its inputs are present, and in others, we can make an output if at least one of its input is present, or there might be other options as well. To see the difference, consider the problem of taking the natural join of 2 relations, R with attributes or column names A and B, and S with attributes B and C. If you are unfamiliar with the concept of the natural join, we're looking for pairs of tuples, one from R and one from S, that agree on their B columns. Any such pair of tuples is spliced together to form a tuple with the A value from the R tuple, the common B value, and the C value from the S tuple. That is, we get those tuples ABC such that AB, that is this, forms a tuple of the R relation, and BC forms a tuple in the S relation. In principle, the inputs are all possible tuples in R and all the possible tuples in S. That is, we assume the attributes A, B, and C have finite domains, and any pair of values, one from the domain of A and the other from the domain of B, could be a tuple of R. So these are one group of hypothetical inputs. Also, any value from the domain of B can be matched with any value in the domain of C to form a possible tuple of S, so these are the other hypothetical inputs. Similarly, the possible outputs are all those triples ABC such that each component is taken from the corresponding domain. In this problem, each output ABC is connected to two inputs, the inputs that justify the presence of that output in the join. Those two inputs are R of AB and S of BC. In practice, the actual relations R and S will have only a subset of the hypothetical inputs. So when we compute the join, we want to make an output ABC only when both of the inputs that join to make the tuple are present on the input. So the actual outputs will also be a fraction of the hypothetical outputs. For example, if 1/10 of the possible tuples of R are present, and 1/10 of the possible tuples of S are present, then we would expect about 1/100th of the possible outputs to be made. The true number of outputs could be different depending on the particular tuples chosen. Now we're going to talk about two parameters that describe a MapReduce algorithm. The first, which we'll talk about here, is the reducer size. Next, we'll talk about replication rate, which is a measure of how high the communication cost is. The reducer size for an algorithm, which we'll denote by Q in what follows, is the maximum number of inputs that we allow for one reducer. Remember, a reducer is a key and its list of values, so we are really putting an upper limit on how long this list can be. One reason we might want to put such a limit on reducer size is so that we're able to execute the reduce function for one reducer in main memory. But there might be other reasons. For example, we might want to put a smaller limit on reducer size to force there to be lots of available parallelism. Remember, hypothetical inputs are assigned to reducers when we design the algorithm. That is, the map function must be designed to generate certain key value pairs, knowing only that its one input exists. We don't know in advance which inputs will be present. However, if we know what fraction of all possible inputs will be present, we can use a value of reducer size that is larger than we want the actual number of inputs to a reducer to be. For example, suppose that we decide we want no more than 1 million inputs to any reducer, and that bound is necessary to enable the reducer to do its work in main memory. Suppose we also know that 10% of all the hypothetical inputs will actually be there when we run the algorithm. Then we might design the algorithm with a Q of 10 million, figuring that the 10 million values that might be sent to the reducer, on average only 1 million of them will really be there, and things will work well in main memory. We have to be a little careful. As long as the problem inputs are chosen independently, then we can expect each reducer to have close to the average number of inputs, and we'll be okay. Maybe you want to set Q a little lower than 10 million to account for the fact that there will be some statistical variation, and we don't want any of the reducers to get more than 1 million inputs. But what if the inputs are seriously skewed, that is, not selected randomly? For example, we're joining R of AB with S of BC, and many of the actual tuples have the same B value. Then it is possible that our strategy for sending inputs to reducer will send many more than average to some of the reducers, and those reducers will cause problems. For example, they may not be able to run in main memory, and the need for repeated disk IOs will make them take much more time than the others. In that case, we have to lower Q well below its expected value. Now let's introduce the other important parameter of MapReduce algorithms, the replication rate. Formally, it is the average number of key value pairs created by one mapper, or put another way, it is the average number of outputs to which an input is connected. For many problems, this fan-out will be the same for all inputs. We'll use R throughout the discussion to stand for the replication rate, and it helps to think of the replication rate as the communication cost per input. The relationship between reducer size and replication rate depends on the number of reducers we need and the input size. If there are p reducers, each receiving q inputs, and the number of inputs is capital I, then the replication rate will be pq divided by I. I should point out that I'm going to make a simplification here to avoid a substantial amount of mathematics. I'm assuming that each reducer has the same number of inputs, and that number is the maximum allowed, that is q. If some of the p reducers got fewer inputs, then the replication rate would be smaller, but usually we get the lowest possible replication rate for a given q by using reducers with exactly q inputs each. Let's see how R and Q relate for the drug interaction problem we discussed earlier. Let D be the number of drugs. In our example, we use D equals 3,000, but there's nothing special about that. Let's also suppose we divide the drugs into G groups of equal size, so each group consists of D over G drugs. A reducer corresponds to a pair of groups, so the number of inputs each reducer needs is twice the number of drugs in a group, or 2D over G. We can figure out the replication rate directly since each drug is sent to G-1 reducers, one reducer for each pair consisting of its group and one of the other groups. We'll assume G is fairly large, so we'll drop the -1 and just say the replication rate is G. Now we have R and Q in terms of G. We can eliminate G and get R equals 2D over Q. This is interesting. It says that the replication rate and reducer size are inversely proportional to each other. That makes a lot of sense. It says the more work we can throw on one reducer, and therefore the less parallelism we get, the smaller will be the communication cost. There might be some confusion with the relationship R equals PQ over I that we learned in the previous slide. Superficially, it looks like R grows in proportion to Q, not inversely. But P is also a variable here, and P is inversely proportional to the square of Q. We can see that the earlier equation for R holds as well if we substitute for PQ and I. P is G squared over 2, Q is 2D over G, and I is D. When you multiply these out, you get R equals G, which we knew from the analysis of what the mappers do. Actually, it's not G, it's G-1, but P isn't really G squared over 2. It's really G choose 2, or G times G-1 over 2. The approximations even out. What we saw so far can be interpreted as an upper bound on the best possible replication rate for any reducer size. In general, when we give an algorithm and analyze its replication rate in terms of Q, we get an upper bound on the smallest possible R for that Q. Surely the smallest R cannot be greater than the actual R we get from the algorithm. However, to really understand MapReduce algorithms, we need to find lower bounds on R as a function of Q as well. The analogy would be sorting on a serial machine. We have algorithms like merge sort that take n log n time on input of size n. That's good to know, but it only becomes impressive because we also have an n log n lower bound on any algorithm that does general sorting. So what we want to address now is how one could go about proving that R cannot be less than a certain function of Q. In order to prove lower bounds and replication rate for a given problem, we need to be able to talk about every possible algorithm that solves a problem. We can't do that in general, but for many interesting problems, we can abstract enough of what any MapReduce algorithm can do that it is possible to make some useful claims about how much replication is needed. So let's define a mapping scheme for a given problem and for a given reducer size Q to be an assignment of each input to a set of one or more reducers. There are two conditions this assignment must obey in order for the mapping schema to be considered as solving the problem with this reducer size. First, of course, we can't assign more than q inputs to any one reducer. But in order for there to be any way of computing the outputs correctly using this mapping schema, there is another condition that must be satisfied. For each output, there is at least one reducer that is capable of computing the output. In order to compute an output, the reducer must have as inputs all the inputs on which that output depends. When a reducer gets all the inputs an output needs, we'll say the reducer covers that output. There are two really important points I want you to bear in mind about mapping schemas. First, from any MapReduce algorithm, we can find a mapping schema. The mapping schema doesn't tell us about the algorithm. For example, it doesn't say how the outputs are computed from the inputs. It doesn't tell us, in a case where several reducers each have all the inputs needed to produce an output, which of them actually produces it. It doesn't say how the mappers generate key value pairs so that the right reducers will get a given input. But we can be sure that if there is an output such that no reducer gets all the inputs that output needs, then the algorithm cannot correctly produce that output. And I also want you to observe that it is the requirement for a mapping schema that makes MapReduce algorithms a special case of parallel algorithms in general. We can't just take any parallel algorithm and implement it as a single MapReduce job. Now, I want to apply the mapping schema idea to the problem of drug interactions and get a lower bound on replication rate as a function of the reducer size q. As we shall see, the algorithm we already suggested for the problem is almost as good as possible. We'll again assume that there are d drugs to compare, and the limit on the reducer size is q. First, the critical observation in all lower bound proofs is to put an upper bound on how many outputs a reducer can cover. In this case, the reducer gets q drug records as inputs. The only outputs it can cover are the pairs of drugs that it has received. There are q choose 2 of these, which I'm going to approximate as q squared over 2. Technically, the exact number is q times q minus 1 over 2, but for large q, there is negligible difference. But among all the reducers, there are d choose 2 outputs that must be covered. Again, I'll approximate the choose 2 by squaring and dividing by 2. So there are approximately d squared over 2 outputs to cover somewhere. So if we divide the number of outputs by the number of outputs one reducer can cover, it's that, we get the minimum number of reducers that must exist. In this case, the number is d squared over q squared. The replication rate is the number of reducers, that's d squared over q squared, times the number of inputs per reducer, that's q, divided by the total number of inputs, which is d. That gives us r greater than or equal to d over q. That is, there is our lower bound on replication rate for any algorithm that solves the drug interaction problem. I should confess that I'm being a little sloppy here. I'm assuming that the algorithm has every reducer getting all q of the inputs it is entitled to. I should do a little more math and consider the possibility that different reducers get different numbers of inputs smaller than q. However, it doesn't matter in the end. We'll still get the same lower bound. Notice that the lower bound, r greater than or equal to d over q, is half the replication rate that the algorithm we described using G groups uses. If you check back to that discussion, you'll find that we had r equals g, the number of groups, and also q was 2d over g. If you turn this equation around, you get g equals 2d over q, or r equals 2d over q, since r and g are the same.